Probability. All right, let's talk about some probability problems. We're going to talk about a couple of different cases and situations here. Um, Go ahead and pause the video and write down these notes that I have here. These are vocabulary terms I'm using over and over again throughout the lesson, so it's a good idea for you to be able to reference them quickly. I'm not going to go through them all right now. You can read. I mean, hopefully you can. You see them in front of you. Um, just know that the probability of a particular event is the number of successful outcomes over the number of total possible outcomes. It's the ratio of success to the total that you have. A couple notes, we typically want to write our probability as a ratio between 0 and 1. 1, if your ratio is 1, that means the probability of that event, it must occur. There's a 100% chance of that happening. It must occur. When your probability is equal to 0, it means that cannot occur. Okay, there's no chance of that happening. All right, so the key thing is for us to really make sure we have a firm understanding of the ways to count. If you remember my 8.6 video, I went over different ways that we're going to count the number of ways that something happens, because oftentimes we'll see that the number of possible ways of something being successful is something that we're going to need to count compared to the number of total possible ways that something can happen. So let's just dive into some examples, which is really the best way to learn a lot of this. So first off, the probability of rolling a 7 on two six-sided dice. So I'm going to say that the probability of getting a sum of 7. Okay, so let's think about this for a second. All right, first off, what are the different ways that you can get a sum of 7? Well, think about the first die, and this is one of the things from my last video too. I realized I was constantly mixing up. Google confirmed it for me. Die is single, dice is when we're talking about plural. So if the first die, for example, is 1, and you want to roll a 7, that means the second die must be equal to 6. So what are the other ways that you can get a sum of 7? Well, your first die might be equal to 2, second one would then be 5. Then you might get a 3, and then a 4. But you might also have the situation where your first die is 4 and your second die is 3, right? That also works, in which case you could also then have 5 and 2, and then also 6 and 1. You can organize this however you want, but I believe those are all the different ways that you could roll a 7 using two six-sided dice. So if that's the case, how many different ways do we have here? We have 6 possible ways. So 6 possible ways of rolling a 7, okay? Now, what is the total? Again, what is the total number of outcomes, of possible outcomes here? Well, again, we discussed this in our previous lesson about the total number of ways, but if you have six-sided dice and you have 2 of them, there are 6 ways you could roll that first die, and then 6 ways that you could roll that second die. And using the fundamental counting principle, we can say that this is simply equal to 6 over 36, which we simplify as just 1 over 6. So you have a 1 out of 6 chance, or we would say that our probability is 1 out of 6 that we would roll a 7. Now let's try another one. Let's try a locker combination problem. So find the probability that your locker combination has only the first number and the third number the same. So again, we're finding the probability that the first and third are the same. Well, let's think about this one. Well, I often try to think of the total number of possible ways first, and then try to think about the number of ways that we can count the successful outcomes. So what are the number of locker combinations that we can have in general using 3 numbers, right? And we said previously that we had 40 possible numbers, so 0 to 39. So we have 40 possible numbers to choose from. And then the second digit could also be, or the second number could be any number from 0 to 39. So you could have a repeat. And then the third number also could be a number from 0 to 39. So you could have, for example, 111 as a number combination. Now let's think about the instances in which we're quote unquote successful, where the first and the third number are the same. So we can choose any number for the first number, right? So we have 40 there. Now that second number, it doesn't say anything about that second number being the same as the first. It says specifically that only the first and the third number are the same. In other words, the second number must be a number that is different from the first. So whatever number we choose for our first number, the second number must be something different. So there's one less to choose from there. Now, finally, in our last spot, because the first and the third number have to be the same, once you've chosen something for your first number, your last number has to be that. So there's only one to choose from there. So this makes it a little bit easier to simplify. We can quickly just divide out those 40s, and we would then say we would have 39 over 1600 is our probability. Okay? All right. Now let's try another one. And I'm going to actually just change this because this is actually harkening back to a real life class that I took where a professor actually, at the beginning of each week, gave everyone a set of 20 review problems. And for the test at the end of the week, this professor just chose 10 of those problems to put on the test. And I know that sounds awesome at first glance, but these problems were really hard. Long story short, there were often many situations where I went into the test not knowing how to do every single problem. So I did spend some time actually trying to calculate the percentage or probability, I should say, that I would pass this test based on how many problems in the homework packet I was able to complete. In any sense, let's try a couple of these probability questions. So what is the probability the student answers all 10 questions correct? Okay, so the probability of 10 correct and 0 wrong. Okay, and this part right here may not seem important right now, but it's important that we actually know how to incorporate this into our work because it will be pretty important down the line. So first off, let's again come up with the total number of ways that something can happen. We are choosing 10 problems, where I'm not, but this professor is choosing 10 problems from the 20 that are available on the test. So ask yourself, what are the total number of ways you can choose 10 from 20? Well, that's just 20 choose 10. There's a combination. Order doesn't matter. Now, what are the ways that you could get 10 of the 17 that you know how to do selected for the tests? In other words, this would be a 17 choose 10 situation, right? The probability of 10 correct, and let me actually do this in a different color. The probability that 10 are correct means you are choosing 10 from the 17 that you do know how to do. And we're going to assume that if you know how to do it in homework, you can do it on the test. Now, I'm also going to write this next part here. So I'm going to highlight this in blue. I'm also going to do this next part here. But you'll see it actually doesn't make a quantitative difference on our answer here. That means if you're getting 10 of the 17 correct, that means of the 3 that you don't know how to do, none of those are chosen. So how many different ways can we choose 0 from 3? Well, we don't really need to know factorials to know that answer. That's just going to be equal to 1. There's only one way you can choose 0 from 3, right? So that is the number of ways that none of the 3 questions show up. And for the sake of time, I'm going to just jump to a lot of the values here. This comes out to 19,448 times 1 all over 184,756, and that simplified would be 2 over 19. Okay. All right, now what about the probability that we get exactly 7 correct? Okay, well, what are we saying here? We're saying the probability of 7 correct and 3 incorrect, or 3 wrong. So we're going to set this up pretty similarly. Our denominator, again, is going to be 20 choose 10, because we're still choosing 10 problems from the 20 that we have available. This time we're choosing 7 from the 17 that we know how to do. And we're choosing 3 from the 3 that we don't know how to do. It's just our luck, right? That the 3 that we don't know how to do, all 3 of those are selected for the test. Well, even without really having a firm understanding of factorials, we should see that this value is going to be exactly the same. Well, why is that? Remember that 17 choose 7 is 7 factorial. Oh, so 17 choose 7 is 17 factorial over 7 factorial times 10 factorial. Well, what did we do in the previous problem? We said that 17 choose 10 was 17 factorial over 10 factorial times 7 factorial. They're exactly the same. 3 choose 3 also is going to be exactly equal to 1. There's only one way that you can choose 3 from the 3 available. So you see that the probabilities should be exactly the same. All right. For this next problem here, I just want to highlight the word at least. And what that means is that we've got the probability of 9 correct and 1 wrong. And that word at least means we have a number of different situations that we need to account for. This also means that we have or the probability of all 10 correct, and 0 wrong, and 0 wrong. Okay, so take that into account. And this is just going to come out to 17 choose 9 times 3 choose 1. I forgot to write the 1 here. Sorry about that. And then here we already did this other part. This is going to be here 17 choose 10 times 3 choose 0. And all of this is over 20 choose 10. And this answer, once you've worked that out for yourself, should come out to 1/2. Now, I want to close this part of the lesson now by discussing unions versus intersections and complements and mutually exclusive events. So a union is kind of what we just described here when we have A or B. And it's important to note, like we just did, that or means addition. So if we have all the different ways that A can happen and all the different ways that B can happen, we want to consider both, right? Now, versus an intersection, compare that. That word and, whenever it's an intersection, this means we're going to multiply. And what this means is that we're looking for the intersection of both A and B. So we're talking about this region right over here. So it's the events that satisfy both the conditions for A and for B. So to kind of give like a real world example, an example of a union situation might be if I ask something like, what is the probability that tomorrow will be warmer than 70 degrees or that it might rain? Now compare that to an intersection where I'd say, what is the probability that tomorrow will be warmer than 70 degrees and rain? Well, obviously the intersection here, we're going to have a smaller probability because it has to satisfy both conditions in order for it to meet that criteria. Complements are exactly what it sounds like. It's the probability that something does not happen, or I should say not in A. Okay, so if the probability of something happening is 8 out of 10, the probability of something not happening obviously would be 2 out of 10. And finally, I don't have it written out here, but I do want to make sure I discuss it. The idea of mutually exclusive events. It's where A and B have no outcomes in common. Have no common outcomes. And we'll see an example of that in just a bit. All right, so let's try some problems with this. So what is the probability if you're choosing one card from a deck? So a couple things you should know. If you don't have a deck of cards, you may want to lay one out in front of you just so you can refresh your memory on how everything works. A deck has 52 cards. There are going to be 4 of each kind of card because we have 4 different suits. So what is the probability that you can choose a queen or a king? Notice this is a mutually exclusive situation. There are no common outcomes between queens and kings. They're completely different cards. So we would say the probability of drawing a queen is what? Well, the probability of drawing a queen would be 4 out of 52 because there are 4 queens out of the 52 that are available. What is the probability of drawing a king? Well, it's also 4 out of 52 because there are 4 available. So the fact that we have an or situation here means we want to add these up. So simplified, this is just going to be 1 over 13 plus 1 over 13, and then we would have 2 out of 13 as our answer. That's the probability of drawing a queen or a king. We're going to be adding those. Now compare that to this next problem. The probability of drawing a heart, which is a type of suit for the card, or a face card. So if I call this the heart here an A event and drawing a face here a B event, notice what's happening here. First off, what is the probability of drawing a heart? Well, since there are 4 different suits, so it's just 1/4, I'm going to write this as 13 over 52. That's the probability of drawing a heart. Okay, so I'm going to write this as A, probability of A happening. Now, what is the probability of drawing a face card? Well, there are 12 face cards, 4 jacks, 4 queens, 4 kings. So that's going to be 12 over 52. That's the probability of drawing a B. So the fact that it says or means I'm going to add these up. The fact that I have or written there means I'm going to add those two probabilities up. However, not so fast. Notice, this time we have an inclusive situation, meaning there are some face cards that are also hearts. And so if I don't do this next part, which is what I'm going to do is I'm going to subtract the cards that are both faces and hearts. If I don't subtract this, I am double counting those cards that are both hearts and faces. So I'm increasing a probability artificially. That's not there. So what I have to do is I have to subtract those cards that, or at least one instance of those cards that are both faces and hearts, so that I don't double count. And what this 3 over 52 represents are the probability of both A and B, okay? And so when I add all those up, this comes out to 22 over 52, and what I have is 11 over 26 as my final simplified answer. Okay, so I hope this gives you a good understanding of basic probability, and we'll then now discuss things like independent versus dependent events.